Assalamu alaikum. Going to get started on lecture 9, this course. The topics discussed today are going to discuss a few, just for your knowledge, how to do feature selection using some more advanced methods that are basically, sometimes you would provide better results. And then we're going to get started on classification methods. I'm not sure if you're going to code anything today, but basically we're just gonna talk about the concepts, and inshallah, hopefully by the end of the next lecture, we're probably gonna have a prototype arrhythmia detection system ready, and we can basically, improve on it in the further lectures, inshallah. So let's get started. So basically for the advanced feature selection measure, let me first review what we did last time. This is what we did last time, basically. This is basically just a set of features that we extracted. We extracted the mean value of each signal. First of all, let me probably just detail what we did last time. Basically, the database, the ECG database we have, has two components, basically: learning and testing samples. They are very different, okay? The learning samples basically are 64 for each type, and the testing samples are 32. We have, for the learning samples, we have 5 different types, and also for this also we have 5 different types, okay? We have to have separate learning and testing signals because basically we need to have different signals for testing other than the ones we use for learning. Otherwise we will have what's called bias. Okay, the system basically bias means that basically using same data for both learning and testing. Like for example, if you're in a math class and you give an example of 5 plus 6 is equal to 11, and then in the test basically you had a problem like this, okay? If you have a problem like this, the student can actually answer it with 11 because he might remember it from the class, okay? Because actually he basically, without even doing the math, doesn't have to do the math, basically. You remember that you told him that 5 plus 6 is equal to 11. So the answer of 11 here doesn't mean that he knows how to do the addition process. So basically, we need to test if he can do that or not. So basically, we have to have separate or a different problem for testing other than the problems presented to the system during the learning process, okay? So basically what we did last time, we started with the first 4 types, basically. We have a database that has the learning samples. The array of learning samples is basically has dimensions of 64 times 1080. This is an array of this size, okay? For a particular type, for the normal and 3 other types, basically, okay? So basically what we did last time is compute some features. Features means that basically for each one of the signals, I just take the samples from the signal itself and just compute a statistical measure, compute a number or a function of the values of this 1080. So for each one of 64 cases, we compute a function of the 1080 samples. And what we said was basically this function right there is basically a feature. Any function you think of. Okay, and we basically had several examples, including, for example, the mean, the standard deviation, the mean of derivative, the skewness, and so many others. Okay, let me run the code from last time, and basically just to see how many features we got. Basically, I think what we have from the from last time, basically we had 39 features, 39 different features. Okay, and basically these 39 different features, we have to test them and make sure that they are actually useful. Useful meaning that they present differences between different classes. Okay, the ones that we basically saw, we plotted plots like this for each one of the features, and the goal is to see a difference somehow between the circles and the axes. If you see a difference, then this feature is useful. If the features overlap, this means that it's not useful. Basically, you cannot predict which class it is from just knowing the name of the value of this feature. Okay, so basically after we did feature extraction, we had basic feature selection. Feature selection, basically we're trying to detect whether what we have is something that looks like this, or something that looks like this. You see the difference between the two? What we need to see is a general trend. We don't not really have to have very wide separation. We basically, the ideal situation, of course, is to have something that looks like this. If you have something that looks like this, you basically have two clusters, this here, and they are widely separated from each other. This is ideal. You will never get that. What you usually get is something that looks like this. Basically, you have a cluster that looks like this, and another that looks like this, and they have some sort of overlap. The smaller this overlap becomes, the more useful the feature becomes. Here, basically, if you try to get the first one looks like this, the second one looks like this. Basically, they are almost identical. Basically, they overlap in most of their areas. Okay, so basically, this is what we're trying to do, whether it's this or that. This is okay, good features. This is not okay, this is bad features. Okay, what we said last time was that we're going to use something called the Ttest. And in particular, what's called two-sample Ttest. Okay, the two-sample Ttest basically takes the set of features, or each features. I take the set of features for the, for example, the normal and the abnormal, and we compare them. The goal is to basically try to see the difference in mean. We try to see a difference in mean value. The mean value of this versus the mean value of the other. Okay, but actually we have to normalize that by also the standard deviation or the standard error. They are related to each other. Okay, so basically if you have two samples, or if you have two distributions that look like this, for example, this is one, this is another. Okay, And you have another two that look like this. They are basically overlapped in basically most of the areas, but here you have much larger variation in each one of them than this one here. This is likely to be okay, this is likely to be not okay. So basically you have to have a difference in mean, and the standard deviation of the data should be small enough to see a separation between the two. In the t-test, we basically test a hypothesis, a null hypothesis, that the means are equal, okay, which means that the normal and the abnormal are just the same, basically, okay, and H1 basically, which is basically the significant coefficient, are unequal, or there is a difference. And the thing that determines the probability of H0 is what's called the p-value, which comes out of the t-test. The p-value is the probability of this useless assumption here. Okay, so if this probability is high, this means that basically H0 here, basically we cannot ignore it. Okay, so usually you take it as significant, consider the feature as significant if the p-value is less than something very small like 0.05. Some people actually take it 0.01 or even less. Some people did do that actually, as usual. But actually the common value that is used is 0.05. It means that if you do the t-test for a particular feature and it turned out to be less than 0.05, this indicates that this feature might be useful. If it's above 0.05, then it's probably not. Okay, this is what we did last time. What we did last time in the code, we just kept, basically we just had a block here where we compute a certain feature, like the mean, for example, and kept copying this code basically over and over and over. And each time we use a different feature, here mean, here standard deviation, here a mean of the difference, which is mean of the derivative, here mean of the absolute difference, here the standard deviation of the difference, and so on and so forth. We kept adding features, and basically we didn't care while we were doing feature extraction. We just add new features and add as many features as we can. Many of these, or some of these at least, will not be useful. Okay, the goal is to have as many starting features as possible, and then we test them using the t-test, and this t-test would let us know if the feature is useful or not. This is what we got here from the results. This is what we got here. Basically, the t-test gives you two values. H, which one, H0 or H1 are the likely hypothesis, meaning that when it's 0, then this feature is not useful. 1, it means that it's useful, and so on for each one of the features. And basically, for each one of these, it gives you also the value of the p-value of each one of them. So basically, the first one here was 0 because the p-value was 0.09. 0.09 is greater than 0.05. The second one was significant because it's very small, smaller than 0.00001. So basically, MATLAB gives you only the first 4 numbers. But if you look at this number, actually, it's not going to be zeros. It's going to be something 10 to the minus 10 or something like that, a very small number. It's actually, for us, it's as good as 0, basically. So basically, this feature is very useful. This one here is 0.07. 0.07 is not significant because it's basically greater than 0.05, and so on, basically, for each one of these features. And basically, we ended up having, basically, for the 39 features that we had, we actually find only 34 useful features. Basically, if you count the ones here, if you remove the zeros from the original count of 39, you will find that 5 of them, 1, 2, 3, 4, 5 features were not useful. So the useful features are 34 only. Okay. What we did after that was just remove these features. because we do not want to go to the classification stage with the features that are not useful. Okay, so basically this is the first method that we saw for basically feature selection. We selected based on the p-value or based on the outcome of the t-test, and that's it. Okay, there are other methods. Let me tell you why people resorted to other methods in addition to that. But basically, t-test is definitely very useful. Okay, but actually there are some issues that we have to consider basically in feature selection. For example, or basically, if I have a feature that is equal to, for example, summation of all points in the signal, okay, square, for example, okay, this is feature number one. I have feature number two is equal to 1 over n summation of n square of n. These are two different features, right? These are different features. Can you see that? Basically, it's the difference between them is the factor here, 1 over n. And this turned out to be, the first one turned out to be significant. And the other one turned out to be significant. Okay? Is that correct? Can I just take these two features and consider them as okay and include them both in the classification process? Just give me your opinion.
I think no, doctor, because it's only scaled by 1 per n.
Yes, basically they are a factor of each other. Basically you have feature one is equal to f, the other one is alpha f, with alpha here is a constant. It doesn't add any further information. For example, if I try to have a policy for admission, for student admission, okay, the students got results out of 1,000 points, okay. So I decided that the policy will have two components. One of them is based on the result out of 1,000. And the other one is the result percentage. Does it make any sense? Basically, it doesn't make any sense because these are factor of each other. It doesn't add any further information. Okay, right? Basically, the result out of 1,000 will be basically equal to this result here times 100 or whatever, 1,000, okay? So basically, if the result here is, for example, 900, it's going to be here 90%, okay? Which means that basically these two are basically just a factor of each other. Just a factor of each other. 90 times 10 is equal to 900, that's it. So this is not useful. So basically, the first issue is redundancy. Okay, redundancy means that you have features that are correlated. This is a proper term, correlated. Correlated means that ideal correlation basically is just what we had here. If you have one of the feature equals to another feature times a constant, then they are perfectly correlated. Sometimes the correlation is not perfect. It's not like a constant factor. It's actually like an implicit correlation. They have something in between or something relevant to each other, but they are not 100% correlated. Sometimes this is a problem also. We have to identify things like that. Another issue is basically complexity. If I wanted, for example, to have an ECG classifier designed on a microcontroller, from what we saw, we had like 39 features to start with. We can add more, okay? if you want to do that on a microcontroller, this is going to be a problem because you don't have as many resources basically to compute all of them. Basically, sometimes you need to limit the number of features. Okay, so limiting the number of features, we try to basically, what we said from the t-test, we said that smaller p-value, basically the p-values of smaller values are better. Okay, so basically here we can actually take, if I wanted to select, for example, M features, take M features with smallest value. The problem actually here, if you want to do that, you can actually do that, and some people actually do that, but the problem here goes back to the problem of redundancy. Because, for example, if you have a feature that has a p-value of for example, maybe I can just write it 10 to the minus 23, okay, and another has 10 to the minus 22, okay, and these two actually are somehow correlated. They are not perfectly correlated. If you are perfectly correlated, you would get here the same exact value for the p-value, but they are kind of 80% correlated, for example, okay? You would select both. But the problem with this is that you got two features, but they are actually not perfectly correct. Basically, they are not providing the extra information that you're supposed to get. So the performance using these features might not be as good as you think. So it's important to try to get the features that are basically that will provide you with the most information related to the classification process. Okay, so now we're going to consider a different problem now. Basically, the feature selection. We're going to start with basically the basic t-test. Okay, so I have, for example, 10 features. And basically use your t-test and they reduce to M features. Okay, M definitely less than N. Okay, it can equal strictly. Okay, basically we need to select. What we're trying to do now is select only, for example, L features, or basically just to make it better or best, L features. And these will be used in classification. How can we do that? How can we get the L result or the L features that will provide the best classification results? Do you have any ideas? This is basically the more advanced feature selection method. And basically the best, actually, the best performance comes from a system that would look like this. How can you do that? I tell you, basically the idea, the first idea is actually, when I tell it to you, actually you find that it's extremely crude. It's actually very simple, extremely, what about if I try, basically I have now M features, okay? What I have is M features. How about if I select L out of the M and keep choosing different L features and trying the classification. and basically selecting the L feature that would actually practically provide the best classification result. How about that? Let me explain it a little bit more. Basically, the problem basically is I need to select L features out of available M features such that classification results are the best. Okay, basically this is the goal. So basically the first crude solution is basically do something called exhaustive search. Okay, exhaustive search means that basically I have M here, take L out of it and try them. And keep doing that, basically. Okay, and basically out of try, select the best. For example, I have now 5 features. A feature F1, F2, F3, F4. I should type it better. The features I have are F1, F2, F3, F4. Let's just consider F4, okay? I need, basically this is M here is equal to 4. I need L equal to 2. So what should I do? I try F1 plus F2. Not plus, I mean with F2. Then F1 and F3. Then F1 and F4. And so on. All the combinations of basically M, select L. We find a long list actually. Basically, this is 4, and we'll end up with a significant figure. By the way, let's just write the math and see F2, F3, because F1, F2 already was there. F2, F4. Then that's it. F3, F3, F4. That's it.
Sorry, Doctor.
3. Go ahead.
How we put the L is to determine the number of L.
Sometimes it's a requirement from the system itself because you need the complexity to be lower than a certain number, or sometimes there is a recommended. Usually for a classification system, it's not a very good idea to have a very large dimensionality. This is something called the curse of dimensionality. People like to have the dimensionality of the system as small as possible. But usually what people do is basically you can also iterate on this. So basically you select L as 2 and then you can select it as 3 or as 4 and basically try and see. But actually for a given L, the problem we're talking about right now, that L was given. But L actually should have a process of selection, how to select the L, whether it's based on the hardware, based on the requirement of the classifier, or whatever. This is another issue. But now we're given M certain number of features, and we are given an L target of number of features to be selected. And basically, the larger the M and the larger the L, you will have very wide variations here of, you have a lot of systems to try, actually. You have a lot of things to try before you can actually make your decision. The the idea is you have 1, 2, 3, 4, 5, 6 combinations, and for each of these, you will use them into the classifier, just train the classifier using these, and basically have the performance metrics. And basically get the results for each one of these. You will select, for example, F1 and F4 because the performance metrics for F1 and F4 turned out to be the best. The advantage of something like this is that you're making your decision based on practical data, basically based on the data content itself. There is a very important point that you have to take into account when you do that, that you cannot do that with the testing data. And you will be biased, basically. The results will have a problem later on. Usually when you do something like this, you do something called cross-validation. Let's talk about first the idea of exhaustive search. If I wanted to select L out of M, I try all the combinations. All the combinations of L features out of these M, I try them all and see which one is best as applied to my data and my classifier as well. Is that clear?
Okay.
So basically the problem with exhaustive search is that you will likely to have very large number of experiments to actually do. Okay, in order for you to reach which one of them is best, you have to try a lot of things. It's an exhaustive search. Basically, usually if you had a computer science class and you had the search strategies, how to search for the maximum or the minimum or whatever, basically if you're trying the exhaustive search method, this is the slowest, but it's definitely the best. So exhaustive search has the problem or the pro is that it gives the best answer. You cannot get an answer that is better than the one you obtain from exhaustive search. The con is that it's basically very expensive, computationally expensive. Computationally expensive, it means that it will take the computer a long time to give you the result. Let me give you a question. Is it acceptable? How can you say that, how can you determine whether it's acceptable or not to have an algorithm that has computationally expensive algorithm?
The hardware requirement, maybe?
Let me put it in another way. Hence, how many times will you do that? How many times do you need to do feature selection? Let me put it in another way. If you're going to implement your algorithm on a microcontroller, are you going to compute or do feature selection on the microcontroller? Are you going to basically, if you want to compute 1,000 features, if you're going to basically compute 1,000 features and select only 2 of them, okay? Are you going to have the exhaustive search to find which one is better inside the microcontroller or what? Basically, go ahead. Okay, basically what you have in the microcontroller, what you will have in the microcontroller is the final selected features. In the microcontroller, you're not going to do the learning inside the microcontroller. What you're going to do is to basically do the learning and the feature extraction, everything, and the feature selection outside. And when you decide which features you're planning to use, you will implement these features only inside the microcontroller. So basically, this will be done once. So if it's done once, then it might be accepted. Because basically, you're gonna let your computer run for a day or something like that. You're just gonna leave it running and basically go home and get some good night's sleep. And in the morning, next morning, you're probably gonna find it not done yet, and probably leave it till the end of the day. And basically, it's gonna take maybe a week to give you the results. But actually, once you got the results, you don't need it anymore. You don't need to do that anymore. You know that features F1, F4 are basically what you're going to basically do best with, and basically just use them in the classification process inside the microcontroller. So basically, it might be acceptable here because you're not going to do it more than once. You're just going to do the feature selection once. Basically, the feature selection is a part of the feature extraction, which is going to be done basically in the learning phase. What you do after the learning phase, that's it. You really use whatever you have. Whatever you came up with in the learning phase, you're going to use later on. Okay? Like, for example, you basically had differential equations or whatever. You had circuits, electric circuits in your undergraduate studies. Okay? Are you going to study the whole course of circuits whenever you look at a circuit? Probably not. You did that once, and basically you apply whatever you learned from that course later on. So basically, if it's gonna be done once, then it's acceptable, it's okay. But sometimes, basically, the computation expense might be a little bit much higher than what you can do. Basically, some systems actually can generate thousands of features, and basically it can be computation expensive that it would take months, for example, to select the features, especially if you have large data sets. So basically, even though the exhaustive search will still give you the best result, you might want to do something that gives you a good result much earlier or with much less computational expense. Okay? First of all, do you understand the idea of exhaustive search, how we do that? Basically, you have 5 options, and you want to try 2 of them. Okay, it's like you have a football team. Okay, you have maybe 21 players. Okay, how can you select the starting 11? Okay, how can you do that? You basically try things, and basically the best 11 that work for you will actually continue to work. Okay, basically, okay, this is basically a very simple idea like this. Sometimes you need more time selecting basically one of the features, but actually, in general, once you selected features that gave you good results, this would be basically it. You're not going to do the feature selection again. Okay, so the exhaustive feature, you just do that. You just try things. Okay, very important notice here is that when you select features, use a different data set from that of testing. So now we said that we have to have a learning data set, and we have to have testing data set. Now, if we're going to do feature selection using this method, we have to have another data set here. What we call it validation. Sometimes validation is a good name, validation set. Okay, so basically for the learning, you do the feature extraction and selection, Then try it on the validation. So consider the validation as the testing that would help you optimize the process here. But you don't use the testing here, the testing set, because basically if you do that, then you bias the testing data. You basically customize your learning to perform well on the testing data. We don't want to do that. We want to have the testing data that is basically very different from anything the system saw during the learning phase. The learning would include the extraction, the selection, and the classification learning process. Okay, so basically it's like a mini test set, but it has to be different. They have to be different. Okay, they have to be different. If they are not different, you're going to get much better results than what how the system would actually perform in reality. Okay, so if you don't do that, if you don't separate these two, if you basically have any mixture of the three, basically if you don't really keep all of them separate, you will have problems in the results. And usually if you're basically writing a thesis or sending a paper using a technique that would combine these somehow or mix these somehow, you will end up being rejected basically, or the thesis will not be basically approved because of that. You have to have very different data for learning, validation, and testing. What we have now, we have the learning set of 64 samples. We have testing sets of basically this is 32. Okay, we have the learning data of 64. Where are the validation data set would come from? How can we get a validation data set if you want to do that? Actually, these are all samples, but actually they are put in a different arrays because basically I want to ensure that these are at least separate. If you want to have a validation data set, you can take a few samples of here or a few samples of here. It doesn't matter. It's up to you. You can basically make the 60 as maybe 40 learning and 24 testing or validation, sorry. Or you can actually take a few samples, but once you do that, you separate them completely. These will be the only learning set, and these will be the only validation set. You're not going to use them any longer as learning or testing. Just keep them separate. How we're going to divide the data between the learning, the validation, and testing will be basically up to our experimentation. So basically, I'm going to ask to try to divide the data in different ways and see which one is better. For example, you can select, instead of having 40 here, you want to have 32 here and 32 here. And test, see if it works or not. You might want to have 50 here and 14 here. You can try that. But the most important thing is just separate them or keep them separate, keep them independent. Is that clear? Okay. So now we would like to propose a few other methods. Basically, you'll find some techniques that people proposed. Basically, faster. Okay, you can say faster selection. Okay. Basically, if you remember the sorting algorithms, some algorithms, the basic algorithm would basically go through all the numbers and basically, yes, maybe just do that and find the maximum, then the next maximum, and the third, and so on, so that you can get the descending sorting going. Okay. Some other techniques actually try to optimize that. Instead of searching this way, you can divide the data into two sets and basically try to find your destination or your target value actually in a much faster algorithm. Here we're going to try to do that. Basically, there is a technique called sequential forward algorithm, and basically there's another one that's called also sequential backward algorithm. Basically, these two techniques are very similar to each other, but they are basically based on very simple ideas. Basically, for the forward, it works as follows. Select the best feature. One feature, okay? I'm talking about the best, meaning the best overall, okay? How can you do that? Just have each feature go through the classification process and see the results for one feature. Okay, see which feature will give you the best results by itself. One feature at a time, just one by one, and select the best one. Okay, then keep this feature. Keep it as F1, as feature number one. Then you start again with remaining features. And basically this time you're going to try classification with two features. F1 that you already selected with the other features, each one of the other features, and see which one will give you the best. Basically notice that for the second one here, it's not going to be working alone, it's going to be working with F1. Okay, so basically you get the best results for the two features, and basically label this as F2. Then you continue like this. Basically you continue like this, select F3 and F4 and whatever until you get the L. So what you do here is you select the first best feature and you see which one of the remaining ones would actually work better with F1. Okay, if you have, for example, if you're looking at the results from the individual features, one of them might give you, the best one might give you like 99%. Or actually, since it's a single feature, actually it's very unlikely to give you a very good result. So basically one of them would give you like 80%. Okay, there is another one that gave you 79%. The second one was 79%. This one here is not likely to be F2 because sometimes this one here is correlated with the first one. So both together, they are not going to add much. When you have another feature that adds, that is not correlated with the first one, you might end up having results here like 85%. If you combine these two, and if they are correlated, you're not going to get more than 80%. Because basically they represent the same information. It's exactly the same as classifying the students with their marks and percentage. They are basically the same. You're not going to get any better classification with these two together. One of them is just enough. So the selection of the second one here basically can be based on, basically it's going to be based on the extra information you're going to add. If you end up here, for example, if you end up with FL having the same results as, or for example, let me just consider F3 and F4. You got results here of 90%, and with F4 it's still 90%, then forget F4, just stop there. Okay, when you find improvement in results zero, after adding a feature, then stop. And don't add the feature. Okay? Because basically I want to get the best results. If the best results can be obtained by 3 features or 100 features, I would prefer to have only 3 features. It makes no sense to add a feature that would give me no information, no extra information, no extra improvement. It would be added complexity without any benefit. So basically, for the forward approach, start with the best one, then best 2, keeping best 1, and best 3, keeping best 2, and so on, until you reach the best L that you need, or basically you either reach that or basically no improvement. If you're asked to get 10 features and at 3 you basically got no improvement, you don't have to provide 10. Basically stop at 3. That's it. Is that clear? So we test the features one by one and see which one's better. I'm not talking about t-tests. Basically, we already passed the t-test. Basically, what we're doing here now is after the t-test. So what we're going to do is try the features in the classification process. Just try to classify using this feature. And basically look at the performance, look at how accurate the results are, and select which feature would give you the best result. Okay, then keep that, and then try to find another one, another match, another one of the other features that would combine with the first one and give you the best result. As I was telling you, the second feature will not be the second one in the individual ones. It doesn't have to be the one that gives you 79%. Okay, you try the other features and make sure that you got a better result than the result that you got from a single feature. If you didn't get higher results, then stop. You don't have to add any other features. If you're using 2 features, even 2 features, when I use 2 features, I got a result of 75%, then it makes no sense to do that. I just use 1 feature and get 80%. Okay? So basically, this is the sequential forward search method. What we call a sequential forward search. Maybe I should add the word search. Because basically, we're searching for which features are best. Let's look at the backward. Backward is has a very simple approach also, but it's exactly the opposite of what we're doing here now. Basically, what we are going to do for the backward is basically start with all features. And basically remove 1 feature, okay, and see the results. If we remove that, okay, should see whether the results are better or not. Okay, so basically I remove each one of the features and see. For example, if I have 10, okay, I will remove first, I will try first from 1 to 9. And then, maybe yes, it's fine, from 1 to 9. Maybe I'll try from 1 to 8 plus 10, and 10, okay? And then 1 to 7, 1 to 8, sorry, 1 to 7, plus 9, plus 10, so on, until at the end you have from 2 to 10. Okay, when you do that, you have 9 features out of these 10, and basically you just remove, here you remove 10, and here is removed. Here you removed 9, here you removed 8, here you removed 1. Just remove 1 and try to classify with the remaining 9 features. The one that gave you the less impact, just remove it. For example, if I got with 9 features, if I got, for example, here, the performance with 10 was like 90%. And with this, I got 90%, and this is okay. I'll just remove 9. And the other ones actually might actually be better or something. Okay? So basically, if I got 90%, I had minimal impact of removing 9, remove it. A feature that affected results minimally, we just remove it. Okay, here it's the opposite. What we're trying to do now is remove the feature that doesn't affect the results. Okay, so basically it's exactly the same. Maybe you can just ignore this here. You don't have to have that. Just select the feature. Just select which one of these gave you the best results. Okay, and basically remove that feature. The goal is basically you continue like this after you select. You move one feature at the beginning. You start with 9 after that. And basically do the same, just remove another, and basically see which one gave you the best result, and so on and so forth. Okay, and basically here you start from the full M. For the forward, was basically 1, then 2, then 3, then 4, then L. So basically one of them you're going up, one of them is you're going down. Here you're going down, here you're going up the number of features. And also here, if you, for example, at M-1 here, you got a certain result, and here you got a result that is definitely worse, then keep these. Okay, you stop here when the results become worse. If you remove a feature and you found that the results are worse, then you stop. You simply stop. Okay, so basically you can implement these techniques to get the best L, or basically the best combination in general. This combination of any number, doesn't have to be L. Maybe just call it X features. Sometimes L is not, basically you wanted L, but actually sometimes it's there is a big improvement if you have L plus 2. Then you might want to consider L plus 2 rather than L. Okay, so basically sometimes you start with a specific L, or you basically target the combination that would give you the best results out of the whole system. Or sometimes you make it like this, the least number of features for same performance. Of M. Okay, so basically, as we were saying here, you started with M. The performance of M feature, even if we have redundancies, basically they have all the features, basically have all the information definitely. So the results from M would likely to be, if they are all significant features after they pass the t-test, then you would expect the result to be the highest if you use M features. So basically, you can actually do the feature selection to see if you can remove one of the features, and you find the results are almost the same as with M features. This means that you remove the feature that is correlated with the other features. It means that its removal will not affect the information presented by the features. Basically, if you have two features and basically they are a constant of each other, multiplication of each other, basically, then if you remove one of them, it's not going to affect the results at all, basically. So I can remove it, I can reduce the complexity of the system while basically losing no performance in the process. You see the difference between the forward and the backward? Both of them attempt to reach exactly what you got from the exhaustive search. Okay, so basically these results, the results of these techniques would give you almost very close results to what you get from the exhaustive search with a much faster process. They are much faster. Okay, if you want to see that, let's consider the example here, the example that we had here in the, basically if you're going to select 2 features out of 4, okay? So basically for the exhaustive search, if you have M is equals, you can just have it as an example. M is equal to 4 and L is equal to 2. Okay. For the sequential forward search, what we're going to do is try 4 times 1 feature. Okay. And then after that, we're going to try how many? Plus 3 times 2 features. So basically, you're going to have 7 experiments. For the sequential backward search, we're going to start with 4. So I'm going to have 1 times 4 features plus 3 times 3 features plus, that's it, plus 2 times 2 features. So this will be what? 2, 4 plus 2 plus 3 plus 1 is going to be also 7. Okay, so basically you just do 7 here. If you increase the numbers, here, and if you notice that here you have lower complexity than the ones that you use for exhaustive search, basically you're going to find that you have computational advantage here. If you use larger numbers, you will definitely notice that there will be a huge difference in the complexity that you need to perform sequential forward search or sequential backward. Okay, so basically these are faster algorithms, or faster, maybe you can say, not approximations, what they call it, faster implementations of the search. Okay? So basically, you cannot get better results using these techniques if you compare them to the exhaustive search. So basically, the optimal case is to get the same results as the exhaustive search. But the advantage is that you're going to get these results at a much lower cost or much faster. Okay? Okay. So basically, these are the techniques, the main techniques that people use. I'm not sure if you're going to implement them, but I would like you to be aware of their existence. I might ask you to do a very simple example of these in the assignment, but it might not, it's not going to be basically applied to the system that we're going to. I'm going to probably give you some data and basically ask you to implement these techniques just, even manually, okay? Just to make sure that you understood them. Do you have any questions? Okay. What I'm going to do now is I'm going to explain a little bit about the classifiers, and then next time, inshallah, we're going to implement them. Okay. Once we implemented them, we basically have an arrhythmia classification system, basically. Okay. And basically, we can get some results, and basically, we keep improving after that. So essentially, inshallah, hopefully by next time, inshallah, by the end of next time, you're almost done with your system. Okay. What we're going to do next is just do some testing, some optimization that I'm going to tell you about in order for you to improve the performance of the system. So now what I'm going to do is talk to you a little bit about classification in general. There's a very simple presentation about classification. I'm going to just go over it. Please stop me at any time, basically. First of all, classification, basically, if you have a system that looks like this, you have the circles, you have the axes. A classifier is basically a system or a surface, a line or a curve or whatever that can be drawn here and basically gives you the classification or the performance, or basically which one of these is class 1 and which one is class 2. Okay, so let me give you an example here from the, you can just go back to the, so we have something that looks like this. This is one of the examples in MATLAB, by the way. This is data, these data are present in MATLAB, and you can actually try them and make sure that they work. Basically, the inverted triangles are basically a class, and the upright triangles, the blue ones, are a different class. So your problem in classification is how to find this surface that looks like this here, that would give you the least error. Okay, so basically, once you have the features, you can start thinking about how to do that. And the problem is, sometimes it's extremely difficult to imagine that, because basically what we have, for example, in our very simple feature extraction, we ended up with 34 useful features. If we keep all of them, you have a 34th dimensional space. Can you imagine 34 dimensions? It's not X, Y, and Z. You have 31 more dimensions than the X, Y, Z. Okay, so it's extremely difficult to visualize. And when it's very difficult to visualize, it's sometimes you have to resort to mathematical formulas so that you can actually try to basically estimate how the surface would perform with the higher dimensional space that you're going to use in your feature space. Okay, so basically what I'm going to do now is tell you more about how to do the classification, or some essentials about the classification. Next time, inshallah, we're going to talk about very specific examples of classification with their MATLAB implementation. First of all, let's talk about the classification assumptions. Okay, so the classification assumptions, in order for you to make sure that the classifier would perform well, or at least explain why it wouldn't work well, basically, you have to have these assumptions. You have to have a visible difference between the normal and abnormal, meaning that if they look exactly the same, then the classifier will not be able to help you. Basically, if we're talking about the ECG arrhythmias, for example, people classify them by eye. Basically, the doctor, the physician would look at the ECG and would let you, or would diagnose the arrhythmia from the ECG. So basically, there is definitely a visible difference. Okay, so basically, if there is no visible difference, then they are all normal, for example. Okay, so basically, if you don't see consistent differences, you cannot program a CAD system, or basically the arrhythmia detection is a computer-aided diagnosis. So basically, you cannot see a difference. Then it's very difficult. And basically, talking about consistent differences, you cannot program a CAD system to see it. And basically, you have to have a training set with both normal and abnormal cases. Otherwise, you're not going to be able to learn. How can I learn to discriminate between normal and abnormal when I'm presented with only normal cases? It's very difficult to do that. Okay, like for example, you have addition and multiplication problems. Okay, and you only learned, or the only examples you saw are for addition. Okay? You didn't see any multiplication problems. Basically, when you see a multiplication problem, you're not going to identify it. So you have to have a training set. You have to train your system with both normal and abnormal cases. Otherwise, it would not learn. Assume also that the features, this is what we have been doing actually in this lecture and the past lecture. We have to make sure that the features actually describe such differences effectively. Okay, meaning that if you have a difference between the normal and the abnormal, the features have to reflect that. If they don't reflect that, then they are not relevant. Okay, so basically, if you have irrelevant features, you will only confuse and misguide the classifier system. Okay, describing such features effectively meaning that basically the t-test is okay. This should be enough. Okay, so basically the t-test would tell you if there is a difference in the mean value of the feature with the normal and abnormal. If there is no difference between the mean values, then they are overlapping. If they overlap, it's very difficult to identify the normal from the abnormal using such features. So we have to remove irrelevant features. Basically, some of the features, basically these are two related. The normal and abnormal cases from distinct clusters or maybe distinct cases or pathologies, okay, that are somewhat apart according to a distance measure. Basically, I'm talking about if I have the normal cluster here and the abnormal cluster, these clusters should be apart. There should be a distance between these two clusters. They cannot overlap. Okay, if they overlap, then there is a problem. Okay, basically they have to have. Basically, I'm talking about the distance measure, meaning that you can take the Euclidean distance, you can take any other distance. But the most important thing is that you can separate them somehow. You don't have to be separable like this. You don't have to have a line that separates them exactly. They can actually be overlapped. But actually, the mean of the first and the mean of the second have to have basically sufficient separation. This is actually one of the things that the t-test looks at. So basically, the t-test is actually, if the feature passes the t-test, then it's a good sign that it will actually pass this one here as well. So basically, if you're talking about intra-cluster distance, significantly smaller than the inter-cluster distance, this would be actually an indication this is a really excellent features. Meaning that if you're talking about, this is the features, maybe I can go it here. You have a cluster for the first feature and the cluster for the second, okay? So basically, this is the center here, okay? So basically, the distance is here between the samples and the center of the cluster, and the distance between the two clusters, basically the intra-cluster distance, meaning that the distance is within the same pathology, or we're saying within the normal, for example, okay, are smaller than the inter-cluster, meaning that basically the distance from here to here, the distance between the clusters themselves. If this is the case, then this would indicate that this will be basically a very good classification. If you want to look at it in a different way, you consider something that looks like this. Basically, you have two clusters or two distributions like this. Basically, the distance between points here are smaller than when you measure the distance between this and that. This distance here is smaller than this distance here between the clusters. Okay, the inter-cluster, when the inter-cluster becomes smaller, then it becomes like this. Basically, you have two cases or two different clusters that look like this. Basically, this is the ideal situation. But actually, this is usually larger, and this is also usually larger. So basically, there is separation. But you still have to have each cluster much more closer to each other, to the samples or the features from the same class must be closer together than their distance from the other features of the other class. Okay, so basically this will be basically a part of the feature selection, and we consider that the t-test will actually give us a good opinion about it, or a good indication about that. So basically we assume that if the feature passes the t-test, then it should be enough for satisfying both of these items. So these are assumptions, meaning that if they are not met, basically you're likely to end up with bad classification results. This would explain why bad classification would happen, or basically the performance of the classification might not be as good. If the results are basically not as good, they are okay, but they are not very good, basically there is some form of assumption here that has been broken. So basically it might be this one here, the clusters are a little bit closer, and the intercluster distance is not much smaller than, I'm talking about significantly smaller. It might not be significantly small, it might be just smaller, a little bit smaller. Okay, so basically this might end up giving you results that are okay, but they are not very good. Okay, so basically whenever we get results from the classification process, we should look at these assumptions and start thinking about which ones are satisfied and which ones are not, and basically conclude or basically write an explanation of the result based on that. So for the classification models, we have basically two main classification models, something called parametric classification and one called non-parametric classification. Basically, in the parametric classification, assuming that the shapes of the distribution are a certain way. Like for example, you're assuming that you have Gaussian distributions, for example. And basically you assume or estimate a model of the classification based on this assumption. Okay, so you assume something about the data, and basically you have a data model. And then you use the data model to basically estimate the parameters of this model. And once you do that, you don't have to you don't need the data anymore. Okay, you can start now using the data model instead of the data themselves to design the classifier. Okay, so basically here you have data. You come up with a model. Once you got the model, you don't need the data anymore, and then design the classifier from the model based on this model. Okay, for example, if I have two data sets, I assume that they have Gaussian distribution. I can basically get the first one, the mean and standard deviation of the first one, and the mean and standard deviation of the second one, and basically forget about the data and just start thinking about maybe it's just and then start thinking about how to classify based on these parameters rather than the actual data. So for example, I can design a classification surface here that is basically the mean of the two means. It's going to be in the center here, for example. Okay, so basically if I do that, I didn't use the data themselves, I used the parameters of the model of the data. Basically, this has advantages and disadvantages. It's usually very good if the data model is correct. But the disadvantage is that it's going to be extremely bad if it's not. For example, if I assume that the data is Gaussian and the data wasn't exactly Gaussian, then the results from assuming the Gaussian model will not be as good. However, if the data were actually Gaussian, then I will get really good results. So basically, this has to be tried. Basically, if I use a parametric classification method, and the parametric classification method give me good results, then this confirms that my assumption about the data model is okay. If not, then I know that the data model might not be as good as I thought. On the other hand, a non-parametric classification here, we start from the data and basically classify right away. Don't model. So basically here we have to keep the data right with me. Basically here I can remove the data. I don't have to have the data. I don't need the data when I classify my samples. Okay, for example, if I did the learning with a data set, I don't need that data set while I'm classifying. On the other hand, for the non-parametric classification, I have to have all the data that I use for learning. I have to keep all the data that I use for learning. I cannot throw them away. Okay. The advantage of this is that it doesn't assume or impose any model on the data, which is actually, it relieves you from the burden of trying to think about how the data looks like and choose the proper model and estimate the parameters of this model. You don't have to do that with a non-parametric classification. And therefore, they call it model-free or data-dependent classification methods. Okay. An example of these, we're going to talk about them, support vector machines. The example of this is something called key nearest neighbor. I'm going to talk about them in a minute. If you want to also categorize the classifier from the point of view of learning, there are techniques called supervised classifiers, where you actually give this classifier in the learning process. You give the classifier the data with their labels. You tell the classifier that this sample is for normal and this sample is for abnormal. Okay? This is why it's called supervised. It's like you have a teacher that supervises you while you're learning. The teacher tells you which one is normal, which one is abnormal. Okay? On the other hand, in the unsupervised classifiers, basically you give the classifier all your data and it tries to find natural clusters. So basically, if you have data that looks like, for example, without any just points like this, just give the data like this to the classifier, to the unsupervised classifier, is going to try to work with the data and find whether there are natural clusters that can be identified or not. And basically, it tells you that you have two clusters. And this cluster has the sample number 1, 2, 5, and 6, and 10, and whatever. And this has the numbers 1, 2, 3, and so on and so forth. The unsupervised would be really helpful to basically discover underlying clusters. So for example, if I have normal and abnormal data for ECG, okay, it can help me discover basically two types of abnormality, for example. If there are two types of abnormality, this unsupervised classifier can identify them, basically. It can actually work with the data and find out these clusters and suggest them to you. Okay, but sometimes it's not as easy because sometimes you don't have as much data, and basically whenever you have a very small data set, it's very difficult to discover anything. Basically, you can barely get the difference between the normal and the abnormal. So basically, what we're going to use in this class is the supervised classification. We will train with our data samples with known labels. We will label normal and abnormal and basically feed them to the classifier to learn which one is normal, which one is abnormal, and basically rely on that to classify unknown cases. Okay? So here the disadvantage of that is that the number of clusters or the number of classes you have is already known. You cannot change it. You cannot discover anything, basically. And basically, it relies on the trainer to provide the correct information. So basically, if I give the incorrect labels here, the classifier will be confused. If a teacher gives the student a problem of 5 plus 6 is equal to 12, okay, then the student will learn that 5 plus 6 is equal to 12. And basically, whenever he finds a problem like this, he might actually, basically, he's going to get confused and basically perform, poorly whenever he has an addition problem because he was trained with incorrect data. Okay, so basically, we're going to make sure of that because basically we have data that are labeled properly. So basically, we're not going to have any problem with that. But we're going to use supervised classifiers, knowing that there are other techniques that are called unsupervised classification that might actually add some more information. The simplest classifier actually is something called the minimum distance classifier. It's very easy, basically. If I have features from pathology number 1, pathology number 2, I just compute the mean of them. For example, if I have a certain feature that I computed from 64 cases, training cases, okay, then I will have 64 values, right? Okay, I have 64 values because I computed one feature for 64 samples, 64 signals. So basically, I end up with 64 values. What I do here is to identify cluster. Cluster basically is just the collection of features from the same pathology or the same class. I identify here the cluster mean is equal to the mean of the features, basically the mean of the 64 cases. That's one case. So this one here is the mean of these values. This one here is the mean of these values, and this one here is the mean of these values. Once you do that, basically identify the center of each one of these clusters. You have this center, this center, this center. If I have a case like this, what should I do to see or classify it? What should I do to just know which cluster this particular case belongs to? In this minimum distance classifier, it tells you to basically compute this distance, and this distance, and this distance, the distance to the centers of the clusters. Okay? And basically it's written here. Basically, if this is the new case, I compute the distance 1, 2, 3, and select which cluster has the minimum distance to this new case and consider it to be a member of this cluster. Again, let's look at this example, this new case here, okay? This distance is the distance between the new case and pathology number 3. Here, the distance to pathology number 2. Here, it's a distance to pathology number 1. Which one is smallest? Which
Number
one?
2.
Number 2? This is the longest.
Number 1.
Okay, number 1, yes, this is the smallest, this is the shortest distance. This is the minimum distance. So basically, I would classify this new case as 1 because of that. It's very simple. Okay. So basically, it's a matter of just collecting the features and computing 1 point. So here you have to keep only 1 point. Okay, the classifier computes the center of each one of the clusters and just keeps them, and that's it. Whenever a new case comes in, I compute my distance, the distance of this case to cluster 1, cluster 2, cluster 3, and that's it. Decide based on the minimum distance. This is a really simple technique, but actually it's not very useful because usually you have overlap. Usually you don't have pathologies or clusters, they are not usually like this basically. If you have overlap between the clusters, like for example, imagine that the same problem that we saw here, we have overlap, okay? So basically, if you have the center here will be where? The center of the blue, say, is gonna be here. Maybe I should write it. The blue center will be here, for example, okay? The red center will be here. When you have an overlap, then basically just consider this case right there. This case is supposed to belong to here. The problem is the variance of this class, the spread of this class is much wider, and so basically this will actually have a much smaller distance to this one here than to this one here. So this will be classified as red class, which is correct, which is incorrect. So whenever you have variance, whenever you have overlap, you will have problems with the minimum distance classifier. Okay? This is one of the issues, but actually you probably want to try it and see if it works or not. This is one of the basically this is a parametric classifier, because basically we assumed that we're going to have a model for each classifier by just the mean of the cluster, just the mean. Okay, so we took all the data and computed the mean and threw the data away, threw the other data away. So here, this is a parametric classifier. You see that? We computed the mean, and this is what we kept. We don't need the data anymore after we computed the mean of each cluster. So basically, after we did that, we basically rely on the means of each clusters, all clusters, to compute the classification result. So this is a parametric classifier. A very useful classifier, which is called k-voting nearest neighbor. This is an example of the opposite type of the non-parametric classifier. Basically, it doesn't do anything, basically. It's the data, if we have data points that look like this, basically the blue ones, the blue squares are a class, and the red triangles are another class. And the green one here is the one that you need to know, need to classify. Basically, it has a very simple concept, actually. Basically, an unknown case is likely to belong to the class of its neighbors in space. Meaning that you basically find the neighbor which one is closest to this one here, which number of cases that are closest, and basically classify this case to belong to them. Okay, the k here is meant to be actually a certain number. We can choose it as 1, as 2, as 3, as whatever. Okay, so if we choose it as 1, it's called nearest neighbor. A special case, basically in this case, we call it nearest neighbor. Nearest neighbor, we look at which one is closest to this here. So basically it's going to be here, of course. This is the closest one. So basically we classify this to that. This is k equals to 1. We can do another thing if we have k equals to 3. Basically, if we have two-class problem, it's better to choose k as odd number, because basically what we're going to do next is to have voting. Voting means that if I choose k equals to 3, then I'm basically selecting the 3 nearest neighbors. And then they are not all the same. Basically, I have voting. Now I have 2 votes from the red and 1 vote from the blue. Meaning that I would also, for the k equals to 3, basically it's going to be red. If we choose k equal to 5, then we actually get the nearest 5 neighbors. In this case, what you're going to get is what? 5 neighbors, 2, 3, 4. Yes? Go ahead.
Blue.
Yes, right. Correct. Blue. Okay. So basically, you know, depending on the choice of k here, you're going to get sometimes different results. But usually, when you have smaller values, as long as you have something that is really close, then it's very likely. If you have 2 cases that basically have very similar features, then they are likely to be the same. So basically, we tried that. We tried the k nearest neighbor with different values here. You can do that through MATLAB. There's a KNN classifier. Actually, there's a different function now because this was in the older version of MATLAB. But there is a function for KNN classification, and we use the k, choose the k. And basically, depending on which one gave us good results, basically you can choose that. maybe if we look at the data that we were looking at here, maybe here also you will have a problem with the k equal to 1, because basically here also the nearest neighbors here might be the red ones. But if you take a larger n, a larger k, you might actually get the good results or get better results for the blue ones that are in the other side. So basically we should try for all the classifiers that we're talking about. Basically we have to try them and see which ones would perform better. It's not basically, it's very difficult to anticipate which ones will do well prior to actual experimentation. So basically these are the kinds of things that we're going to be doing, inshallah. So I think I just wanted you to just learn about the parametric versus the non-parametric, just for very simple examples. And basically, inshallah, next time, I prefer to stop here so that just give you some time to just absorb the concepts. Next time, inshallah, we're going to try them on MATLAB, okay? I hope the other code that we started with, including the features, feature extraction and selection, is well understood, because next time, inshallah, we're going to continue on it. We're going to add the part about the classification. We're going to add several classifiers. And later on, we can also add the part about the metrics, the performance metrics. They are very simple, actually, to add. There's a function in MATLAB that would give you the confusion matrix right away. And basically, from the confusion matrix, there are very simple equations that we saw in the table for the performance metrics that we're going to just implement. Okay, so hopefully, inshallah, next time, at least we will have a single classifier, at least the minimum is one classifier added to the previous code, so that we can have a system for arrhythmia detection for ECG arrhythmias, okay? And basically later on, we're going to maybe add further classifiers, or basically change the parameters of each classifier so that we can check whether the performance is better or not. So the optimization basically will be the task that you're going to do in this research problem, basically. Okay. So do you have any questions?
Thank you, sir. If you don't mind, I want to ask you about the lecture 8 code, if you don't mind.
Yes, go ahead.
Exactly, I tried to run it, but it's not work with me.
Actually, you have to have the data in the same folder. Did you have the data in the same folder?
Yeah, I tried to put it in which file I can find that data.
The data is in the research problem 2 RAR file.
Yeah, I put
it. Are you sure that it was there? What was the problem? What was the error that you got?
Let me see it again. Don't mind.
Because sometimes the difference in version, MATLAB version, might cause you some errors, but it's very simple to solve, actually. You just tried the code as is. You didn't change anything, right?
Yeah, that's the same code. Change the MATLAB current folder or Ttest folder.
Yes, you have to change the MATLAB folder in order for you to run it from the location where you have the data. You just do that. So basically, if I run it here, maybe I'll have to ask you about this. Do you get an error?
The data, ECG data reader. Okay.
You got an error?
Yeah, Doctor.
Can you post it in the chat? Just go to the chat area and post it there.
Okay. Copy it. And they will be posted in the sheet.
Just copy it and paste it. Don't try to
Okay,
write
yeah.
it.
Okay. Yes, Doctor.
Yes, it's the same error I was telling you about. Okay.
Yeah, I know, but I tried to find the database for that one.
Where did you try? It's present in the RAR file that I sent you.
There is no RAR file. You sent to us only the code.
No, it's given in the RP2 data. It's in the research problem 2 data.
Oh.
Okay, that's fine. I'll post it in the same folder. That's fine. That's no problem. Okay.
If you don't mind, and lecture 7 also. There is one code for the other one. It's the same problem.
Yeah, basically, this is not a problem. Basically, it's not able to find.
I know.
So it's not a problem.
Okay.
No problem. You can send me an email about this right away. I mean, you didn't have to wait for the lecture. I mean, it's yeah, I can basically post it right away. Don't worry about it. Okay, so I'll post it. Okay.
Thank you very much, Doctor.
No problem. Do you have any other problems? Any other problems for the other students? Okay, so we'll stop at here. This lecture, inshallah, we'll continue next time with the implementation of the classification process. Okay?
Okay, thank you.
Okay, shukran. Assalamu alaikum.
Assalamu alaikum.